Hey, how's it going? All right, so today we're going to do a demo on multimodal fusion in Colab. Um, so, welcome to my channel. This is Chef, and it is June 12th, 2024. One thing I've been doing a lot is I've been talking about multimodal fusion in general. And I've been talking about like more advanced models like CLIP and models that have essentially been um, productionized for multimodal fusion. I've been talking about things like late fusion, early fusion, middle fusion, etc. But I think I wanted to do a demo on actually demonstrating how one could actually build a fusion pipeline, a very simple one for a few different cases. And so that's this attempt here. So what I'm going to be doing is I'm going to use a few different data sets. I'm going to start with the CFAR data set, which is a data set of several small images, I think like pretty pixelated. And it's pretty much used as a benchmarking data set to help classify, to see how well your classifier is doing. It's actually pretty easy to classify all the images in the CFAR data set. So what I'm going to do is going to use that same multimodal classifier that I fabricate for CFAR and see how it performs against the Stanford dog data set. Okay, and I've done this already, so I'm just going to go through the code and how that's set up and the results. Okay, so basically we have a multimodal classifier here, the first multimodal classifier for CFAR. The first thing to note is that we're going to be using common models for each of the individual modalities. So for the image modality, I'm going to be using CNN, a convolutional neural net. And for the text modality, I'm going to be using an LSTM, a long-term, short-term memory network. And that's for, usually, it's pre-transformer. It's a much older model. And I could use a transformer model here if I really wanted to, but I just wanted to demonstrate that this is possible with simpler models. So essentially what I'm doing is I also have this noise factor here where I can introduce some random noise to an image. I'm not going to really go over that too much. I just decided to add this here because I wanted to try at some point seeing if I could degrade the image and still do classification. That's one of the things that I like trying out with new classifiers, but we'll focus on that later. So the first thing I did was create from several of the labels from the CFAR data set, I created pieces of text, and then these texts, I am turning them into text embeddings. I'll show you where I do that, but this text is going to be my input text into, this is going to be my training text for my LSTM. And then, so I take the text and I essentially tokenize it so that I can actually input it into my LSTM as features. Tokenizer is just a simple text feature creator. So I turned these into a feature that can be input into the LSTM and also combined with the convolutional neural net. And here is where I'm using the LSTM to do the actual work. So the LSTM itself is again, a pretty straightforward, a small parameter, small model. This is again a simple data set, so it doesn't really matter that much, but the embedding, the text embeddings that are fed to the LSTM will help inform in the fusion step the model and create this shared cross-modal embedding space. So that's the basic LSTM part. And so for the actual image classification, I take the CFAR images, the CFAR 10 images up here. I'm loading the CFAR dataset, and I take these the CFAR images, and then I use a convolutional neural net to do feature extraction on them. Note that this is a very simple convnet, actually. This is a convnet with 2 convolutional layers, 2 pooling layers, and 1 dense layer with 32 nodes. And then your output. But we'll talk about that in a moment because that is actually part of the fusion pipeline, fusion stage. So yeah, so the the convolutional layers are doing all the hierarchical feature extraction for the image, for each image. And finally, what happens is that I have my image and text embeddings, and now I use this concatenate method, which is meant for this first purpose of concatenating the embedding space of two different modalities. And then I continue the learning on a standard MLP. The rest of the pipeline is just a dense layer, 32, I think a 32 node dense layer. And the output's 10 nodes for 10 output classes, and we use the softmax activation function to turn those into actual class probabilities. So we're using standard categorical cross entropy here still. We're not going to go do anything fancy with the actual cross-modal matching functions or anything like that. We'll just keep it simple. And then when I run the output, you can see that I get the classifications here. So you see that there's some incorrect ones, right? Specifically, many of them are correct. Most of them are correct. Cat is cat, ship is ship, ship is ship, frog is frog, cat is cat, frog is frog. In this case, frog is horse for some reason, and airplane is airplane, but automobile is deer. And that's weird to confuse that with a deer. But one thing I can do is I can do something simple here and just change the number of training units that I use to run this. And what this should do, pretty simply, in a moment's time, is, because again, this is the CFAR data set, so this is a simple toy data set to test the classifier. Let's see, this should output, yeah, much better classification. Everything looks like it should be here. Okay, so anyway, the point is this was a simple multimodal classifier. And you can do this kind of classification without the multimodal element. It's just that the multimodal classification is kind of the point. So you're building this shared fusion pipeline. Now, if I use the same classifier as above, the LSTM CNN classifier, what ends up happening, right? I'm using it on a more complex data set now called the Stanford Dogs data set, which is a bunch of cute dogs of different categories. I guess the Stanford dogs. I'm sure it's from Stanford. So the Stanford dogs I'm using the same kind of classifier, LSTM, to create text embeddings. Creating text embeddings and then using an LSTM to do the text classification in the as a multimodal fusion input. Then I'm getting the image classes from the Stanford Dogs dataset and creating text embeddings, or I'm creating text pieces out of them, which I then create text embeddings. I do the same thing, take my image through the convolutional neural net, take that input, and then take the text pipeline, concatenate the two things, and create, then finally do the rest of the learning and classification on the rest of this pipeline, which is just the dense layers. And then finally, what happens at the end of the day is that here's my Stanford Dogs data set, but what you can see is that the accuracy is actually pretty horrible. I have only 0.12% accuracy. So if it's a Welsh Springer Spaniel, it sees a Brittany Spaniel. It got the German Shepherd, but the Labrador, it thinks it's this other thing, Basenji. That's a dog type, don't hate me. The Bloodhound, it thinks it's a curly-coated retriever. The Bernese Mountain Dog is a Pembroke. And what did it get right? Almost nothing. It only got one thing right, the German Shepherd, which I guess stands out amongst dogs. This one, wow, okay. All right, so the thing is, it's obvious that the multimodal classifier isn't really working in this case. So what we need to do is beef up the base classifiers. And specifically in this case, this one's an easier solution. We can beef up the base image classifier because the image classifier was a non-pre-trained plain vanilla ConvNet. And so we know that ConvNets have come a long way, and we can use something slightly more advanced, or fairly more advanced, which is a VGG net, which is the visual geometry group ComNet, which is a ComNet that was trained on the ImageNet data set. Okay, so with that being said, we do the same thing with our text embeddings. One other thing that we do here that I did specifically to make this easier is to do some data augmentation, because I think, it's going to, without data augmentation, Stanford dogs is generally difficult. Even with a good pre-trained network, there isn't enough variation in the default classes to capture all features associated with different orientations of the dogs, and different heights, different perspectives, etc. So what I can do here is create a synthetic data set using image data generator, and it'll skew and stretch and do all sorts of convolutions to the dog, or rather affine transformations, if I'm being more correct, more exact. And so what happens is I now create this class. I'm creating this class called Multimodal Data Generator. And Multimodal Data Generator is basically going to take the original image batch, augment them, and then stuff it into the pipeline. Okay, so that's one of the important things here, is that the data is got to be modified, and then we're going to have to extend the training based on these augmented images, which are all these scale differences. And then finally, what I do is then I I have the same thing going on. I'm changing slightly one other thing using this so-called global average pooling 2D, which is a technique that's more advanced than simply just using the neural network base interconnections. You can look it up. It actually does more, but essentially it does a more intelligent reduction and more efficient training and output of the data set in the embedding space of the network. And so I have my LSTM as above, create the embeddings. I have my image is as below. I create the input, image input, and then finally I concatenate them against a multimodal classifier, multimodal pipeline, and then do the classification. And lo and behold, I wouldn't show you this otherwise, the results are much better. The Welsh Springer Spaniel is a Welsh Springer Spaniel. So is the German Shepherd, as per before. The Labrador is a Labrador. The Kelly Blue Terrier is a Kelly Blue Terrier. Burmese Mountain Dog, and so on and so forth, and everything looks peachy keen. Okay, so that's basically multimodal fusion. It's not a very complex example of multimodal fusion, but it's showing you how you can use a concatenation step to do the multimodal fusion. Okay, thank you very much.